It's a great pleasure to be here in Cambridge and to be invited to give a talk about something I've coined 2 years ago at a TED Talk in Edinburgh. It's Li-Fi, which stands for light fidelity instead of Wi-Fi. And the reason being that we use a totally different media to transmit data. And why we do that, I'll give a little bit of a tour through that. And I've also spun out a company that's here on the right side, POVLC, where we try to get this technology to market at the moment. So we have heard about big data this morning at a panel. Here's some evidence that big data is going on. This is, for example, YouTube, where you can read the lines here. Every minute, 72 hours of video is uploaded via the YouTube channels. And interestingly, most of that data that is sort of sent through the networks is 25% comes from mobile handsets, from smartphones, tablet computers. So while we could generate this data and put it somewhere and put it on a lorry with a bunch of memory sticks, I think this is not practical. So somehow we need to transmit that data through some networks, and that network has to carry all this load, which is increasing. And video is one of the major drivers for big data that is sent through networks. And that is growing at an annual, or a compound annual growth rate of about 50%. So this is real, this is ongoing. So we are seeing that happening. And then I have two graphs here that try to reflect that growth in data onto what's going on in wireless networks. And so on the right-hand side, what I show you is a graph from Qualcomm where they showed the different wireless communication standards from GPRS, which is 10 years ago, up to LTE, long-term evolution. 2x2 means two antennas at a transmitter, two at the receiver. It's called MIMO, multiple input, multiple output. So this is the latest version sort of you could get at the moment. So and what is plotted there is the so-called spectrum efficiency. That's the number of bits that are transmitted through 1 hertz of bandwidth. So you have a certain channel, 5 megahertz channel, and you want to maximize the number of bits you can press through that water pipe to this data pipe, if you want. And this is the efficiency. So as a German, I'm quite sort of keen in talking about efficiency. Sorry for that. So, but what we see here is in about 10 years, 13 years ago, the efficiency was 0.03, so 0.03 bits per hertz bandwidth transmitted through networks, wireless networks. And that luckily has increased to 1.4, which is about a 50-fold increase in the usage of spectrum. But the trend here, what we see is what is important. We don't see an exponential increase. That efficiency saturates, despite tremendous technological developments in communication systems to their advancements. On the other hand, on the left-hand side is data from Cisco, where they basically show what I've showed you with the first slide. Data is increasing every month, and it's increasing at an exponential rate. So if you look at 2012, there's about 1.3 exabytes per month sent through mobile networks. Who of you knows what an exabyte is? It's 10 to the power of 18, so 18 zeros. And look at this in the year 2016. It has increased by a factor round about 10-ish. So increased by a factor of 10 in about 4 years, and that is tremendous. And the problem is that wireless spectrum doesn't grow at the same rate. Efficiency saturates. So what happens if you just do a little bit of unscientific comparison about trends? Exponential increase, saturation. What's the problem? Spectrum crunch. So we're running out of spectrum. We are running out of capability of transmitting data through our networks in order to enable the Internet of Things, machine-to-machine communication, video uploads, all these great things that create so much wealth in the world is limited by the spectrum crunch. So the solution is simple, very simple. 3 steps. You would, first of all, need to identify new spectrum. If you have more spectrum, you don't worry about efficiency, just more. But sadly, we don't have it in a certain region, in the RF region. We can enhance the reuse, the reuse of spectrum. Again, comes down to the efficiency. In the past, in the second generation, we had GSM, where the cell radius was 35 kilometers. In LTE, the cell radius is 200 meters. So the cells get smaller, smaller, and smaller. And that concept of smaller cells was, in fact, the main contributor for that increase in spectrum efficiency I've shown you earlier. It's not about new technology. It's about getting things cramped into smaller spaces and getting smaller cells. And use the same frequency more often in a sort of a spatial context. Obviously, this requires new infrastructure, requires cabling, and now we end up in a problem of wiring up all these base stations, so-called backhaul problem. But we can do both of these measures together. So the first point, if we have identified this is a problem and that's the only solution, what would be the natural step to do? We look into the electromagnetic spectrum. What is there? Obviously, this lower part here, this is where all the radio frequency communications engineers are interested in the radio frequency spectrum, high frequency, ultra high frequency, and so on, up to 30 gigahertz. That is sort of the first boundary line there. That is what is currently used because of the good propagation conditions. But now researchers start looking into that region, the 30 gigahertz region, and they call it millimeter wave communication. Researchers start looking into that region here, terahertz communication, but there are sadly no devices that can be used in that region. But if you go up the spectrum, you will identify, you would easily find that region here, so infrared, the visible light spectrum, which is part of the electromagnetic spectrum, has the same properties in terms of its physics, but it is 10,000 times larger than the entire radio frequency spectrum we have. 10,000 times larger. It's unregulated. No government has its hands on that spectrum. It's free. It's safe. Not yet. Somebody here from a government? No, hopefully not. It's free, safe, it's unused. And we are using it in the incarnation of the LED-based light bulb. LEDs are electronic devices like transistors, and they have similar properties. They can be switched on and off in a very, very rapid manner. So we have them, and they save hundreds of nuclear power plants if we would replace the heating systems we have in the ceiling in the form of incandescent light bulbs by more energy efficient LED light bulbs. But not only that, these are electronics. So why don't you put your electronic gadget into the ceiling rather than a heating device, where this electronic gadget can do more than just illuminating the space, can give you data at hundreds and hundreds of megabits per second. And you would use existing infrastructure. You wouldn't worry about building up new base stations inside rooms, malls, shopping malls, universities like these. You just use the wiring that provides the energy to these light bulbs. In fact, there's a standard by Cisco, it's called Power over Ethernet, where they have reversed the philosophy. They provide data to a point, and the power comes on top of it, at the back of it. And this is something that could be used here as well in order to provide data to the light bulb. So if you have your 2 points there is where your power and data comes in, and here is your transmitter. And that provides data at very high speeds. And I told you that the main contribution to the increase in spectrum efficiency in RF was the small cell concept. But we know there are physical limits. You can only have so many Wi-Fi routers in a room, because if you put multiple Wi-Fi routers in that room here, for example, they would interfere with each other and would basically take away capacity from each other. So you can't do that. But on the other hand, if you look at like a room like this or a room like this, you have many light bulbs in the ceiling. And if you take this light bulb here, it would illuminate a certain space there. It would have little impact on a light bulb in that corner here. So there's little interference from one transmitter to another one inside the room. So you can pack much more of these so-called optical attocells into a room. And that's why you could increase the so-called area spectral efficiency. The other advantage is light wouldn't penetrate through walls. So you would have no interference in the other rooms. And that would give you much more capability of reusing that light spectrum, which is, again, free and unused. And that's why I called it attocell network, in sort of continuation of the idea of femtocells, smaller cells, smaller, is the attocell. And we have a twofold gain. So first of all, if we would replace lights by LED light, we would save energy anyway. But we would also save energy in terms of not needing additional energy to communicate. This would basically come on top, basically for free. And we would exploit existing infrastructure, which is an investment benefit, as well as a barrier to market reduction benefit. So this is a bit of a science bit I've done here now. My background is the mobile communications, and I've been working in that area, in that industry, in that field for 25 years. And I've been looking at RF systems. So what we have done is we have, with a client in Japan, have modeled a network, a cellular network, as you see here, where we have radio base stations, so-called macrocells. And then we have an indoor office environment like this. This is a 5,000 square meter indoor office environment, which is split into rooms, office rooms, and then we have corridors. And then we have done a computer simulation where we have added femtocells, so existing femtocells to this story. And then on top of that have further increased the cell radius with our attocell network here, where the light bulbs in a room would provide data that would communicate with the users. I need to tell you at that point, I had a TED presentation 2 years ago where we showed a video from an ordinary 1 pound Osram LED light bulb. And in the lab, we've achieved 130 megabit through an ordinary LED light bulb. So this is the regions, or the numbers we are talking about. So what we have shown here, again, this is the only plot I show you. On the x-axis, we have the number of femtocells per floor in this network. And on the y-axis, we plot the area spectral efficiency. This is the number of bits per second per hertz per square meter. And we compare that area spectral efficiency with the area spectral efficiency of a pure RF femtocell network. So if you see a number 1,000 here, this would mean that you get 1,000 times more bits per second per hertz per square meter if you would use the attocell network. And in fact, you see this number here. If we only apply 4 femtocells per sort of 5,000 square meter office environment, and we would, on top of that, have the LED lights that provide data, we would have about 900 times improved area spectral efficiency. Compare this with a 50 times improvement of spectrum efficiency over the last 13 years from GPRS to LTE. This is magnitude higher. And even if you would be desperate in adding more femtocells to your RF network, even at 20 femtocells per office environment, the gain at the end would still be 100 times improvement in area spectral efficiency. So if your LTE system, in fact, in this room, you wouldn't get any LTE signal, at least not from 3. If it would be 1 megabit per second, if you applied the lights here, you would get 1 gigabit per second. So you could, and in this room, you could have video streaming at 1 gigabit per second. And you could, in parallel, watch all your nice videos when you see a boring dog like mine, so to be distracted from that. So yes, you could have much more possibility to transmit data. I give you now a bit of a vision that we have as part of our company of how we integrate Li-Fi into Wi-Fi, where we have a Wi-Fi router, we take the Wi-Fi router, plug it into the home plug system via power line communication, and then use the power line network in order then to provide data to the light bulb. And this is meant to be illustrated, via a little video, and to give you sort of visual ideas. So I hope this illustrated a little bit so where we see the future. And in order for me to wrap up this talk is that I believe that auto-cell networks will be the glue between energy-efficient illumination and wireless communications, and why don't we merge both trends? It harnesses unregulated, unused and vast amount of electromagnetic spectrum that hasn't been used for data communication so far. And it would enable the ever smaller cell concept in order to provide us with this tremendous increase in data rate demand. And it would achieve a 3 orders of magnitude and even higher increase in the spectrum efficiency. So that concludes my talk, and thank you very much for your attention.